Welcome everyone to our first talk in November, organized by South Asian Linguistic Society that we have recently formed to promote research and education in linguistics, specifically in Bangladesh. Okay, so today we are glad to have Professor Nathan Hill, who is a historical linguist and also works on Tibetan and Semitic languages. Today he is going to talk about Saussure phonology and vector semantics in contemporary NLP.
Most people will be familiar with who Ferdinand de Saussure was, and in some ways, he's considered the founder of linguistics. Certainly, let's say before him, all of linguistics was historical linguistics, and then after him, we got different branches of linguistics like phonology, morphology, syntax, and so on. So there is a picture of him. And he actually he wrote two books in his life, one when he was the age of 19 and one after he had died. Yeah. So he did not think he was a very important scholar because the first book didn't get a very good reception. And his first book was about laryngeal theory in Indo-European reconstruction and was eventually everyone agreed with his ideas. It took about 50 years. And then he taught in the last few years that he was working and alive. He taught a course in general linguistics to undergraduates. And then when he died, his students published it as a textbook, kind of in his honor. And that's this book, the Cours de linguistique générale, which sort of started it started the movement of structuralism, which of course went into anthropology and all sorts of areas outside of linguistics, but then also kind of is where modern linguistics comes from. So we just want to remind ourselves of a few points of Saussure's teaching. One is the so-called langue versus parole distinction. So parole is maybe what I'm doing right now. So what people actually happen to say in performance of their I don't know of their talking to each other, and then langue is the system that in the system of a language, it's grammar, it's lexicon that allows parole to happen. It's the kind of system in which we move when we're speaking. And this is oftentimes compared to the Chomskyan distinction between competence and performance. But I would say that there's a big difference philosophically, which is competence and performance is personal, like my competence and my performance. Yeah. Whereas long and parole are more society wide. Like long is the thing that is, as an abstract entity is latent in parole, and parole is the actual body of communications as practiced by human beings that is made possible by the fact that language is a system. If there was no system to language, we couldn't have parole. So they're a kind of dialectical unity and a little bit different than the Chomskyan idea. Okay, anyhow, oops. Okay, so I move ahead, and then this is Saussure's notion of the sign, and this is a very famous, picture of a tree. Yeah, so this is taken from his textbook, although in the textbook, of course, it was in French. So the sign has a dual nature, which are the signified and the signifier. And the here, the tree, the word tree is representing the signifier, and the picture of the tree is representing the signified. So the signifier is expressed in sound. Here it's, this we when we make the picture, we have to write letters, but the idea is the word tree kind of considered in the aspect that it's the sound tree, that's the signifier. And then what is the signified? The signified is the meaning tree. But we have to be very careful here because the sign as a whole is the word tree. And then the meaning tree is the meaning tree. It's not a tree in the real world. So it's a little bit confusing, I think, to people sometimes that there's a picture of a tree, because then it makes you think, oh, the meaning of the word tree is a tree. But that's not quite right. The meaning of the word tree is the meaning of the word tree as a unit in the system of language, right? So I'll talk a little bit more about that. Yeah, so the I just emphasize this. The signified is a meaning. It's not a thing in the world, right? Trees are things in the world. The meaning of the word tree is a meaning in social practice as languages are used. And then this relationship between tree and the sound tree and the meaning tree is arbitrary in the sense that different languages have different sounds. Yeah, so in German they say Baum, in French they say arbre, and more or less they're using those sounds to do the same work. And I think that's the way I would say it. The work that's done by the word is its meaning, and then the way of doing that work by saying the word is its sound. And then it's arbitrary, but historically contingent, right? So we can't just wake up one morning and decide to call trees something else. That's not how the world works. And I think that, when I was young and postmodernism was very in style, we all like to talk about how things were arbitrary and socially contingent. But I think we've a little bit lost sight of that things around us that are arbitrary and socially contingent are also historically given. So you can't just, pretend they don't exist and they go away. You have to actually, change them through practice. Yeah. Anyhow, so I like to think of a sign as a tool, like a saw, for instance. So a saw has two parts. It has the blade, that is what I use to cut with, and it has the handle, which is how I, control the saw, right? So in this case, the sound tree is the handle. It's by making the sound tree and by hearing the sound tree that I'm able to use the sign tree. But the work that the sign tree does is, the role it plays in communication. Yeah. So that's the actual, blade of the saw is the function of the word in a system of communication. Okay. Now, uh, another sort of key point of de Saussure's theory of signs is that a sign has no positive identity, right? And this is kind of related to the fact that the meaning of tree is not a tree in the world. If the meaning of tree were a tree in the world, then I could say the positive meaning, the positive identity of tree as a signified is a tree. But instead, what it is a series of negative relationships. So all the word tree is the fact that it is not any other word. Yeah. When we use tree, we're using tree. We're not using bush. We're not using flashlight. We're using tree, right? And these sets of oppositions exist both at the level of the signifier and the signified. So yeah, so the constitution of the signifier is merely its set of contrasts with all other signifiers. And then I can't help, because I was a Sanskrit major as an undergraduate, mentioning that there's a school of South Asian philosophy called Apoha, which is extremely similar to this. Basically, that all concepts are they're the contents of a concept is merely the negation of its negations, right? So like the idea of a tree is the fact that a tree isn't a bush. Yeah. So this was also a theory from pre-modern India, or I should say pre-modern South Asia. Yeah. Right. Okay. So just going with the negative contrasts that create the signifier, we look at this in terms of sound, right? So house is different than the word louse because one starts with an H and one starts with an L. And house is also different than the word mouse because house starts with an H and mouse starts with an M. And house is different than spouse because spouse starts with a sp and house starts with a h. And so, this is a relatively, maybe it seems like a trivial point, but it's the fact that house is a different word than mouse, which is it as a word in English, right? And in this case, because of minimal pair, it's only the difference between H and M that's allowing house to be a tool in social practice, right? And then I give hound and howl also because then you can see that this set of negative oppositions is multidimensional. House contrasts with louse in that it starts with an H rather than an L, and it contrasts with hound insofar as it has a different rhyme. It's aus instead of ound. Yeah. Okay. So that's the multidimensional set of kind of negative oppositions that creates house as a signifier, right? And then okay, yeah. So I've just said that the Constitution. Well, no. So now next we move to from the signifier to the signified. So the constitution of the signified is also merely its set of contrasts with other signifieds. So now we are in the realm of, let's call it, meaning. When I say house, I am not saying dwelling. I am not saying abode. I am not saying mansion. Yeah. So these are words that have a similar meaning to house. Now, maybe I'm being a little bit recursive in terms of what do we mean by meaning? Well, what I would mean is, in a social context or a sentence, in terms of syntax, where you could use house, you may often also be able to use dwelling. And the choice to use house is a choice not to use dwelling. Yeah. So it's the opposition between dwelling and house that is what constitutes the meaning of the word house. Yeah. And then I also just say, for these first three examples, dwelling, abode, mansion, house, I'm saying that, the use of house and the oppositions between house and other words in terms of the signified is what creates house as a signified. But of course, it's also the case that a house is not a bucket or a dog, right? So this this opposition through negation, distinguishes house not only from dwelling and from mansion, but from all other signifieds. Yeah. Okay. So now we've covered the two planes of the sign, that sort of two, if you think of it as a coin, the two sides of the signify, sorry, of the sign, the signifier and the signified, which, like sides of a coin, can't be separated from each other, right? If I say tree or house, I'm also meaning tree and house. It's a sound and meaning, yeah? So now I want to look at another kind of set of oppositions, which, using de Saussure's term, are the associative, let's call it plane or dimension, and the syntagmatic dimension. So these are basically, intuitively, the words that uh, can go in similar places but cannot be together with. That's what associative is. And syntagmatic is words that can't go in similar places but do occur together with. Yeah. So I'll just give some concrete examples. Yeah. So let's start with associative. We call it in absentia because, like, let's say, to use my example of like house and dwelling. Like, if you're using house, you're not using dwelling. So they have an associative relationship, which you can think of, although it's a little bit hand wavy and imprecise, as psychological, right? Like I have the idea of house, and if I say the word house, then I'm not saying the word dwelling, right? So they're two words that could substitute in the same slot, but precisely because they could substitute in the same slot, they can't both be there. So one is absent, and that's the relationship of absence. And then examples. This is from Saussure, are things that yes, let's say morphological families. So like if I have the word teaching, enseignement, uh, then if I'm saying enseignement, I'm not saying enseigner, enseignant, enseignant. These are other forms of the word, yeah, or morphologically related forms, but that can't go in that syntactic spot, yeah. And then I'm also invoking, these semantic relationships, like apprenticeship, education, instruction. And then also there's a sort of formal dimension, which is like enseignement has a mall, and it can go where it goes, partly because of that mall, which is an adverb, or no, sorry, it's a noun in this case. And then there are other nouns that end in mall, like uh, armament, change, government. Yeah. So those also are words that could go in that slot in a sense, but don't. So in all these cases, I'm deciding on a word, and that means I'm deciding against words that could go there. Yeah. Okay. Now we come to syntagmatic relationships. These are words that kind of often go along with a word, right? So there's a syntagmatic relationship. So syntagmatic means kind of put together, yeah. It's as in syntax. So these ones are present, yeah. So we say in presentia is in using the Latin. So a syntagmatic relation fixes a value by its linear combination of units that go along with it in the same chain, right? So if I say like public education or public teaching is changing, l'enseignement public change, one thing that characterizes enseignement as a word is that it can happen before the word public, right? So these are all just dimensions of this negative opposition, right? In a sense, that like, how do I know where I am? It's because I'm in front of my computer, or maybe I'm in front of my computer and I'm behind my chair, right? So these are the dimensions in which a word is in opposition to other words. One is this one that if this word is there, then other words can't be there. Yeah. And then in this case, if this word is there, other words are likely to be next to it. Okay, so then we have this like four dimensions, I mean, dimension is maybe the wrong word, but we have association and or an associative relationship, a syntagmatic relationship, and then we can have those for the signifier and for the signified, which are basically formal versus semantic, right? So enseignement has these associative relationships with other words. Uh, and then there are syntagmatic relations, like that enseignement is composed of a root and a suffix. And then also there's this at a higher level of abstraction. There's different words that can go to the right and left of enseignement. And then in terms of the meaning dimension, there are words that have a similar meaning to enseignement, so kind of could maybe go where it goes. And then there are words that kind of can come before and after enseignement, and then in a certain sense have a similar meaning to it in that they can modify it or they can precede it or something like that, right? Okay, so that's basically now we're done with de Saussure and sign theory. So I sum up and say that meaning and form are values determined by contrasts within a certain system. And then the pairing of signifier and signified is arbitrary, and what matters is these oppositions and these distributions. Yeah, sort of what is someone's place in a system, right? Like, so I'm a professor in Dublin, and I don't know, I'm single. Yeah, so something like that. Like that means that you have certain relationships that define who you are. And kind of if you sum over those structural relationships, then you have a pretty good characterization of someone. I'm American, I live in Ireland, I'm a friend of Zacharias, I'm giving a talk in Bangladesh, yeah. Uh, and then you don't, if you define something through these sets of oppositional contrasts, then then you don't need in a sense, a positive characterization of something if you know its place in a system. Okay, but let's stick to signs. Yeah. So this is the point I was just making. A sign has no metaphysics. Yeah. It doesn't point to anything in the world, and in a sense, we don't need a theory of meaning if we have this understanding of signification. And what meaning is, another way of putting it, is the place of an item in a web of contrasts. Okay, so this is a negative definition. Each element is what the other elements aren't. Yeah. Now, when ChatGPT became, popular, like whatever it was, a year and a half ago or something, and even a little bit before then, I was thinking about this new development in NLP, which is basically the term to keep in mind is transformers. And now I think hear the word transformer, and I think of things in like electrical grids, and that's not what we're talking about. It's I'm not going to talk about transformers, but it's a thing Google invented in around 2017, and there's a certain like way of storing of extracting information from training data is the way to think of it. But anyhow, it's what underpins this kind of new style of NLP, which is all the rage these days, right? So when I first heard about it, I thought it's a complete vindication of de Saussure's theory of the sign. And when I went around and people were saying, "Oh, ChatGPT is so dangerous because now all the students are cheating," I would say, "Yes, but isn't it wonderful that it has vindicated Saussure's understanding of the linguistic sign?" And then they looked at me a little bit funny, and then I struggled to characterize exactly what I meant. Yeah. So then I was very lucky because I ran across this article where it's a sort of 60-page article that very clearly lays out this intuition I had already had of how it is that the impressive performance of LLMs vindicates the structuralist or the Saussurean understanding of the sign. So I will mention, I didn't want to just copy this guy's paper, turn it into this talk. So I haven't reread it since I read it, some time ago, and instead prepared this talk myself or with me and ChatGPT worked on it together because I felt like that was appropriate since I was talking about LLMs, right? But now I'll move on. But I'll say I will say I really like this piece, and actually I sent it to Zakaria some time ago, and that's partly when we got talking why we decided that I would talk about this. So okay, now I will talk a little bit about how the back end of LLMs work so that you can, at least I can kind of sketch out for you why I think that they're a vindication of Saussure and his theory of signs. And it's not going to be, I don't really know, I can't make an LLM, I don't really know how they work. But I know a little bit, and that's what I've put in this presentation. Okay, so let's start with what a vector is, yeah, because I'm going to need to use the word vector. So a vector is one column in a matrix. And what's a matrix? A matrix is a bunch of numbers arrayed, in front of you in a table. So a vector is one column of numbers. So here you have it. V equals V1, V2 to VD. And then we can call D the dimensionality of the vector, right? So let's say the intuition is like, let's say I'm characterizing a point in three-dimensional Cartesian space. I would say where it is on the x-axis, where it is on the y-axis, and where it is on the z-axis. So it's a triplet of three numbers. Okay, so a vector is like, to use the math term, an n-tuple. So it could be 2, it could be 3, it could be 500 million, but it's a certain number of numbers that's in a column. Okay, so quite simple. But as I've just kind of hinted at, another way of conceptualizing a vector is an arrow. So like here, our vector v is an arrow that is v1 in the x dimension and v2 in the y dimension. And then you think of it as going from 0 to some point. Yeah. So this is just, it's mathematically identical, right? But we've changed we've changed the way we're looking at our column of numbers, where each number is understood as specifying a point in a particular dimension, and then the dimensionality of the vector is the number of dimensions we're playing with. And it's easy to imagine or see when it's two-dimensional and maybe three-dimensional, but you can have 5 or 10 or 50 dimensions, yeah? And then you can still imagine that a vector is an arrow from 0 to a particular point in a space of an arbitrary dimensionality. Okay. And then we can characterize that arrow by two things. Its length, uh, which is, its magnitude, its length, how long it is, how far from 0 it is. That's what I was trying to say. Yeah. And then the other one is its angle, which is to say, how is it, different in direction from other possible vectors. It doesn't have to do with how far it is from 0 it's how far it is from other vectors of the same length. Yeah. So you can use those two ways of characterizing a vector. Okay. And then I have to just define, but we'll move very quickly away from it, then something called cosine similarity, which is basically the angle between two vectors. And that's all I'm going to say, is it's the angle between two vectors. It's one way of understanding how similar they are. If two things have a very small cosine similarity, is that right? Very small, yeah, very small cosine similarity. Then they are, no, sorry, it's right here. Interpretation one, yeah, it's a measure that goes between 1 and -1. So if it's at 1, then they have the same angle. If it's at 0, then they like have no relationship in their angle, and if it's at -1, then they kind of have the same angle but are pointing in opposite directions. So cosine similarity is actually I think this is one of the things that makes it convenient is it's between 1 and 0. So you can say these are very similar or they're less similar, but you can intuitively understand it as a measure of the angle. Okay. So why are we playing around with vectors at all? Yeah. Well, if we can so let's put it this way. This de Saussure way of talking is very hand wavy. Yeah. It's not like, oh, abode is different than house, is different than dwelling. But how can we get to grips with it kind of from an engineering perspective? And I think that's really what has happened in the last couple of years is we have gotten to grips with it from an engineering perspective. And we do that by characterizing these things in as vectors. Yeah. So basically, if you can model something in the world mathematically, then you have a bunch of off-the-shelf tools to deal with that object mathematically. Yeah. And then you can do things like compute the similarity of two words using their representation in a vector space. Okay. So let's just go through this. So distances can reflect similarity in distribution, and directions can be understood as stable relational contrasts. And I'll talk through this concretely, so don't worry if it just sounds like word salad at the moment. And then also, and I'll come back to this later, the absolute coordinates aren't what's relevant. What matters is, how different vectors are related to each other. Okay, so now I'm going to go through this sentence. The quick brown fox jumped over the lazy dog. Oh, I thought I had written it down, but I didn't. Okay. Anyhow, this is a sentence that we use to practice handwriting, right? Because it has all the letters of the English alphabet in it. So I'm going to encode it different ways from less sophisticated to more sophisticated. So in the first case, we build a vocabulary. I think we have 9 words here. So it's a 9-dimensional space. And each word in the sentence we represent as having a location in this 9-dimensional space. So the word quick is 0 in the dimension the, and it's 0 in the dimension brown, and it's 0 in the dimension fox, and it's 0 in the dimension jumped, but it's 1 in the dimension quick. Okay? So that's our first approximation. Quick is the word that has the value 1 in the dimension quick and the value 0 in all other dimensions. Okay? And then the is, in contrast, the word that has the value 1 in the dimension the and a value 0 everywhere else. Yeah? So this may seem silly and tautological, and that's because it is. But it gives you a sense of we're moving towards representing words using vectors, yeah? And this captures identity, right? So dog times cat means you'll have a 1 times 0 in one column and a 1 times or and a 0 times 1 in a different column. And so you get 0, which is just telling you cat and dog are different words. Yeah. Okay. And this is called one hot encoding, which I find a very funny term. But the reason why it's called that is because there's one spot in the vector which is hot in the sense that it's the only one that matters. Yeah. Okay. But this doesn't give us any information about meaning. Yeah. So let's try something that's a little bit more sophisticated now. So we're going to take the quick brown fox jumped over the lazy dog, and we're going to build a sentence vector by summing the one hot word vectors, which we can call counts. Yeah, and this approach is called bag of words. And the reason why it's called bag of words is because we're totally ignoring syntax. So we just take all the words and we throw them in a bag. Okay, so now in our sentence, we get this vector. So this is this is the vector. And one thing that's nice about these vector representations is I can sum words into sentences, right? I can take the vector for quick, the vector for brown, and I can add them up and then get a sentence vector. Yeah. So this is our vector for the quick brown fox jumped over the lazy dog. It has in the dimension it has 2, right? Because we have the quick brown fox jumped over the lazy dog. Yeah. And then in all other dimensions, it has 1 because quick comes up once, brown comes up once. And if you wanted a higher dimensional space with a dimension for philosophy or government or Bangladesh or something, then those would be zeros. Yeah. But we're going to stick with this small vector space. So anyhow, so then we've done it. I've just shown that we can represent, sentences as the sum of words because we're representing words as vectors, so we can sum those as a sentence vector. Okay, but it's still a little bit coarse. Yeah, how are we capturing meaning? Well, we're not really yet. So let's move from identities to coming up with co-occurrence windows for context. So here we use a symmetry window around each target word. So we're looking at 2 words to the left and 2 words to the right. And now we look at the quick brown fox jumped over the lazy dog. And so we look at the and its context window because it has nothing to its left. Yeah. So its context window to the right has quick and brown. And then quick has the to the left and brown and fox to the right. And brown has the and quick to the left and fox and jump to the right and so on, right? So we just go through these and now we see that our 2 thes in this representation are different, right? Because the first the has the content, if you like, quick and brown, and the second the has jumped over lazy dog. Okay, so now how do we turn this into vectors, right? So so let's do it. Okay, so here's what we call a co-occurrence matrix. Yeah. So now you look at well, let's look at quick first. Yeah. Okay, so you see this is the same information but encoded in a matrix. So quick has the to its left and it has brown and fox to its right in this 2-word context window. So then we mark its kind of vector representation as +1 the 0 quick brown 1 fox 1 jumped 0 over 0 lazy 0 dog 0. And then some of you are probably saying, but wait, it's in the same sentence as dog. Doesn't that somehow capture some information? And yes, it does, and we'll get to that. But for now, we're only looking at the 2-word context window. So we're saying it's quick really likes the word brown and the word fox and the word the, but dog it's very far from. Yeah. Okay. So then you see how basically exactly what I presented on this slide. I've rewritten in a matrix form on this slide, but with one caveat, which is in this case, I've collapsed the two thes. So we can represent, we're getting more information from by adding both the fact that Quick and Brown were in its context window and the fact that Jumped Over and Lazy Dog are in its window. And actually, already now you can imagine that we just read all of English literature doing this, yeah, and then we will be able to characterize slowly each word in English in terms of the context windows that it co-occurs with in some kind of high dimensional vector space, right? Okay. Now, what's the disadvantage of this? The disadvantage is that everything will be of very high value in the space, right? Because the is a really frequent word. So we've gotten to the point where we're basically able to take a distributional phenomenon and turn them into math. But now we want to normalize is the word, I guess, against frequency. So this is how we do it, and this is where things get a little bit mathy. And I'm sorry about that. Is that the slide I wanted? No, yeah, okay. So this we use something called pointwise mutual information. And I just want to give you a sense of what it means first. So we want to, yeah, so if two things have zero pointwise mutual information, that means they have no relationship with each other. Yeah, like you choose two people randomly on the surface of the world. They will eat in different cafes. They will have different friends. They will have different jobs. They have no relationship. They will have zero mutual information. You can't learn anything about one of them by watching the other one. Yeah. Whereas uh, if two people are, for instance, married, or something, then they live in the same city. Maybe they even work at the same workplace. They have the same children. They maybe watch the same movies because they're spending a lot of time together. So that means if you have information about one, you can predict some information about the other. They have high mutual information. So that's the intuition. And then you can also have negative mutual information. And I'm going to use the example of Dr. Jekyll and Mr. Hyde, right? So Dr. Jekyll and Mr. Hyde are the same person. So if you're at a cafe and you see Dr. Jekyll, then you're not going to see Mr. Hyde, yeah? So they actually have negative mutual information, yeah? They are avoiding each other. So now how do we actually define it? Now, in a second. Okay, yeah. Okay. So, this was the slide I meant to show. Sorry. So, pointwise mutual information, greater than chance, about the same as chance, or less than chance. Okay. And then this is a way, if we know this, it's a way of filtering out right? Like the fact that, I don't know, quick occurs with the a lot is still not telling us anything about quick because the occurs with a lot of words. So point-wise mutual information is a way of normalizing against frequency. And then here's how it's actually done, and I'll just kind of read this. So the mutual information of two things, W and C, is the logarithm of their joint probability over the multiplication of their probability. So if you see, if their joint probability is higher than the product of their independent probabilities, that means that they have some special relationship. Yeah. Okay. And then I've just the next line just defines each of these things, like what do we mean by probability of W and C, and what do we mean by probability of W, and what do we mean by probability of C, and you can see that this is just summing over other probabilities. I'm not going to talk more about the math. If you like reading math, you can read it. Yeah. But then I will mention that people don't actually seem to use pointwise mutual information very much. Instead, they use positive pointwise mutual information, which basically says I take the maximum of either zero or the pointwise mutual information. So basically, I'm deciding to ignore the Dr. Jekyll and Mr. Hyde situation. Yeah. So if the mutual information is negative, I pretend it's zero. Now, I don't quite know why that's what we do, and certainly if you're doing like phonology, if you're looking for minimal pairs, you shouldn't do that, right? You should find complementary distributions, which will be negative mutual information. But I think the notion, like I was thinking about this kind of as I was having my lunch a few minutes ago, and I think it's like, imagine, like, it's very hard to imagine in English, like, what's a word that absolutely cannot be used in the same sentence as some other word? It's very hard to think about. So, maybe it's like two schools of science have like two different words for the same idea, like phlogiston and or dephlogisticated air and oxygen. You say like, well, probably dephlogisticated air and oxygen are not going to occur in the same sentence because either you're an oxygen theorist or you're a phlogiston theorist. But actually, I just used them both in one sentence. So, so that shows that I think these kind of Dr. Jekyll and Mr. Hyde things are very rare and probably just artifacts of randomness. So that's my intuition of why we use the positive pointwise mutual information. But I don't know, maybe someone in the audience knows more about that than I do. Okay, anyhow. So now using mutual, so yeah, so I didn't say it, but now basically we calculate the positive pointwise mutual information based on the corpus, and then slot that in for the value at each point, right? So like if we go back here, I'll say rather than saying quick the one, I will actually calculate the mutual information between quick and the, and I'll put it in there, and then that's where, and then those will be fractional values or sort of decimal points, and that's how actually people fill out these vectors. Okay, so there's just one little problem that we have, which is if we're talking about, doing this with English, English has like 100,000 words or something like that. I don't know, maybe more than that, maybe 150,000 words. So if I want to, tell the computer the word butterfly, I have to go through the whole corpus of my training data and calculate the mutual information between butterfly and all other words. Yeah. Uh, and I will be operating in 150,000 dimensional space. And that becomes computationally unwieldy. Our computers will all run very slowly if we're doing these calculations in 150,000 dimensional space. So there's actually a lot of gaps in such a space, right? Because I don't know, because it turns out that dephlogisticated air and I don't know, Victoria's sponge cake just just don't ever interact in the corpus. So then, lots and lots of gaps will occur, and you'll have these very spacious matrices. So then, if you have that, and now I'm talking about in a very sort of abstract mathematical way, I can smush them down. I have so much space in my space that I can smush it down without losing any information, and then my computer runs faster. Yeah. So that's what we do now, which is we reduce dimensionality. So what does it mean to reduce dimensionality? Well, this is what it means. We take the big positive pointwise mutual information co-occurrence matrix and we keep its k most informative directions. So we just look at how many dimensions are giving us most of the information in the matrix, and we only keep those dimensions, and we throw out the rest a little bit. Yeah, yeah, and then this is where I go through this in more detail, which I won't talk about. But let's just say, for those of you who know about matrices, what we're doing is factorizing matrices. So we're seeing, can we represent a big matrix as a product of smaller matrices? Okay. And now I'll just show you a kind of mock-up of a projection, right? So we have this gigantic, crazy 150,000 dimensional space. It's very hard for us to imagine, but what we can do is we can slice it in a lower dimensionality, and here I slice it in 2 dimensions, yeah, and that process of slicing a high dimensional object in a lower dimensional manifold is called a projection, and you just notice that that's like with maps we have, we have I forget the name, but like different projections. That's why Greenland always looks so big on maps, right? Is we have some way of changing a 3 dimensional globe into a 2 dimensional map. That's a projection. Okay, so here we have this projection, and we can look at the cosine similarity, which I talked about earlier, as the angle between the arrows, and then we notice that quick and lazy are close to each other, yeah, because they're both adverbs and have to do with maybe speed or something like that. Uh, so yeah, and this gives us a tractable mathematical definition of similarity, right? Okay. Uh, and we can notice that many linguistic relations appear as parallel offsets in the space. So, for instance, plurality, right? Like we have a point for cats and we have a point for cat that are just calculated from the math, yeah? And then there's a vector that will bring you from cat to cats. And that vector is parallel in geometrical terms to the vector that brings you from dog to dogs. So now we can understand plurality as a shift in our geometric space that brings cat to cats and dog to dogs. Yeah. Uh, yeah, basically I'm just showing you that like now we've changed, linguistics into geometry, yeah, in a sense, yeah. And then here's another one which is analogy, which can be thought of as vector addition. So we have something like king minus man plus woman equals queen, yeah. So you start at where, yeah. So I start at king, and then I shift it over by the amount of man. Uh, sorry, no, yeah, I minus man, then I add woman, and then maybe I've ended up in the geometry near queen. I've tried this with Tibetan a little bit, and the results are sometimes odd because usually, if I actually do this and take king minus man, add woman, I don't precisely get queen. I get a vector that doesn't exist in the language. Yeah. And so what then you ask the computer to do is find the closest actual vector to that one. And because you can understand that like we have expressions like queen bee or drag queen. Yeah. They don't correspond to king. So the math will have kept track of those differences, but probably if you do it, you'll end up with queen being the closest outcome to king minus man plus woman. But anyhow, if you have enough data and you've put it all in your computer, you can play this game and see like in what cases does my analogy get me what I predict as a person, and what cases it doesn't. Okay, so basically that's it. Like, well, I don't know. I haven't quite said how ChatGPT works in terms of how it is that it takes a prompt and gives me a response, but actually that's quite easy, which is it takes my prompt, it turns into a vector, and then it looks at the geometry in the space of the language and says, if this is the first part of like if we're on a path, like downhill, which is Nathan's prompt, what should I say next? Yeah. And and it just looks at the geometry of the space it's in and says, I think a good answer to that question would be this. Yeah. And that's also why you get hallucinations. Hallucinations happen in a kind of gappy area of the geometry where like, I find that when I ask ChatGPT about ablaut in the history of the Tibetan verbal system, it seldom gives me the truth. That's because I know more about it than it does. Yeah. But it is correctly like a person. The way to think of it is, it's like a person who feels awkward in a conversation. It's just like, oh, what do I say now? Yeah. So it just makes it up based on the math, and whether or not it gives you the truth or whether or not it gives you a hallucination depends on how densely populated that part of its geometry is. Okay. So why is this Saussurean? Yeah. Well, the value is by difference. Positions are defined by contrast with neighbors, and coordinates only matter via relations, right? We have no ontology here, right? The only thing quick is a different dimension than brown, and then we look at the behavior of people's language as a social totality. We sort of spy on everyone and listen to what they say, and then fill in our matrices with that information. But there's no representation of real objects in the real world in any of this. Yeah. And then there are analogs to the associative versus syntagmatic relationships. So associative are things like nearest neighbors or substitutes in this space. Like, so if I have a certain vector, what are the closest actually existing vectors that are nearby? And then syntagmatic are these co-occurrence constraints, like cat versus cats. You can think of them as the kind of context that creates structure inside the geometry of the object, which is a high dimensional manifold called English. Yeah, and it's arbitrary and invariant in the point that, like, we decided that whatever the was dimension one and quick was dimension two, but it's totally arbitrary. Yeah, you can assign any, like which dimension numerically. The order of the dimensions is arbitrary. You can scramble them all up, and it will work anyhow. At least before we reduce the dimensionality. Once you reduce dimensionality, you might run into problems. But in any case, so this vector geometry gives a concrete, measurable form of de Saussure's relational view of language, and that meanings emerge from structured contrasts across the lexicon. Yeah, and then why is it that LLMs work? It's because distributional learning recovers much of the meaning, that is relational structure. So basically, LLMs work because de Saussure was right. Yeah. Okay. And then here are my conclusions. Yeah. Sort of for the philosophy of science, we can reject a correspondence meaning of truth, right? So, what I say? I don't know. Roses are red means that roses are red. That's Tarski's, truth as dequotation. Like, we don't need it. Yeah, we don't need the real world in a sense. Yeah, at least as a model of what knowledge is. We don't need the real world. Uh, we don't, or I should sound less anti-realist. We don't need a correspondence theory of truth, and theories of truth are unfashionable in philosophy anyhow, right? And then for linguists, I would say the fashionable way of doing semantics is model theoretic Montague semantics, which has a correspondence theory of truth built into it, right? I take a sentence like elephants are green, and then I paraphrase it in first order calculus. So I have such like for all x such that x is an elephant, x is green, and then I interpret the meanings elephant and green in some model theoretic space, right? So I would say that's a stupid way of doing semantics. Yeah. For two reasons. One, because I'm a structuralist who's a Saussurean, and so I just have like doxographical disagreements with it. It's not my camp. Yeah. But also, they haven't made LLMs. Yeah. So, so I would say that the structuralist distributional understanding of meaning has like works in reality, right? And the best test of our scientific theories is, do the bridges hold up? Do the airplanes fly, right? And so far, we have one school of semantics that makes something that works and one that doesn't. So I would say let's move away from the correspondence theory of truth and from model theoretic semantics. That's my conclusion. Thank you very much. Okay, so just on that narrow question, think of these things in the dimensions that you have intuitions about, right? If you imagine like an x-axis and a y-axis with something at a 45-degree angle, right? Then the dimensionality is two because we have x and we have y, yeah? And then the direction is 45 degrees, yeah? And if we have a point that's, let's say, uh, one on the x-axis and one on the y-axis, and you draw a line between 0 and the point 1, 1, then it's at a 45-degree angle. Yeah. So all we're doing is that. It's like it really is. That's we mean dimensionality in the normal meaning, and we mean direction in the normal meaning. It's just that uh, most people, and I include myself in them, do not have intuitions about what things look like in more than uh, two dimensions, or no, three dimensions. Yeah, but you can understand it, as just like degrees of freedom, right? So, like, if I'm a one-dimensional, if I live in a one-dimensional world, the only thing I can do is move left and right. Yeah. Whereas if I live in a two-dimensional world, I can move anywhere except up and down. Yeah. And then if I live in a three-dimensional world, then I actually live in the world I actually live in. Yeah. So what does a four-dimensional world look like, for instance? Well, actually, if you ask the physicists, we may live in a four-dimensional world where the fourth dimension is time. So the fact that, I continue to exist from one moment to another is maybe the fourth dimension. But you can think of it as a degree of freedom. So if you had like four, five, six dimensions, then you could like reach through a brick wall because you would just move, around the brick wall in some higher dimension. Yeah. Okay. I mean, it may sound very abstract, and actually it is. Like this is a silly way of thinking in a sense. Like, um, what happens is the way, let's say, math works as a discipline is you find some real thing like a field, and you're trying to argue with your neighbor about who owns a particular tree or something. So then you develop a practice of measuring the field. But once you have that practice, you can make it more abstract, and now you can measure five-dimensional fields. Yeah. Okay. So it's just a way of, kind of coming to grips with like doing something with the words so that you can keep track of the information. Yeah. And I would say think of dimension as degree of freedom. Yeah. And then direction is best understood as meaningful within the geometry of a space you've defined, right? So in a two-dimensional space, then the direction is just this way or that way. Yeah. Um, but we can do these projections like you saw, where you take the high dimensional space and you flatten it down into like two dimensions. And then the only risk there is that, and you can sort of imagine this in a three-dimensional space. Let's say I have a point up here and a point down here, and then I smash them into two dimensions. It could be that things that are actually very far away will look similar. So that's a risk with projections. But I don't know about how the projections are actually done. But anyhow, before I just sort of mouth off about these things, I will say about, is ChatGPT actually thinking, or understanding? I would say, of course it's not. It's a machine, and and in the same way that, like your example, birds and airplanes do not fly in the same way, right? But I would still say that an airplane embodies a lot of human knowledge about how flight works. And that is demonstrated by the fact that they fly. Yeah. But it's not the same as a bird, and it's not intended to be the same as the bird. It's a human tool used to, achieve human ends. And I think that the idea that's very popular in America these days that what is it called, general intelligence or something like that, is just silly. Yeah. They're machines and they do what they're, built to do, and they're super useful, like making slides or cheating on your homework. Yeah. So the answer is actually that there's some really good free or not very expensive courses online about machine learning, like at Udemy or Coursera, and then you can take kind of just an introduction to NLP um, or a machine learning course on one of these platforms. And I actually think there are a lot of advantages to that over doing it in a university course because it's first of all much cheaper, and then you can also do it at your own pace. And I find, at least if Ireland is anything to go by, if you actually take these things in university, they spend a lot of time on the theory at a very high level without actually showing you how to make anything. So I think if you're interested in kind of making these sorts of things, then it's good to start with like one of these kind of MOOC style things, or even just YouTube videos. What I will say is it's all geared towards English. And I will tell you from personal experience, we try and make something for Tibetan, for instance, and you start having problems at the very beginning. Yeah. And it's a constant fight that all of the tools were built making certain assumptions like that there are spaces between words or that sentences end in periods. Like it's not the reasons that NLP is hard on some languages are tend to not be theoretically interesting. And that's precisely why the computer scientists never help us solve them. Yeah. So I would say like the way to kind of come at the intersection of linguistics and the sort of engineering side of this stuff is just learn the engineering stuff in the normal off-the-shelf way for English, and then learn the linguistics in the normal off-the-shelf way for linguistics. And then in your own mind and in your own body, you have to bring them together, right? Which you do by concretely trying to solve problems, right? So like in my, I don't know what to say, my students and postdocs, we've worked on things like handwritten text recognition for Newar, which is a language of Nepal, and automatic speech recognition for various languages. And I think like that's really where you bring the engineering and the linguistics together, is in trying to actually build a tool that actually does something in relationship to a specific language.
Yeah, maybe I can ask one small question, Nathan. So when you were discussing the math, and I could relate it to, I'm not sure whether it's related or not, but I can see that a lot of it comes from the collocational values of different words and the distributions, right? And what we do in collocation is to see the number, the frequency of different words occurring together. So do you see at some, I mean, it's related, right? So the collocational values of different words, appearing with whether they are, but in that sense, we see the positive values. So you were talking about the negative values of whether two words or different words, several words can co-occur or not, if I'm not wrong. And the second question, maybe you could tell when you were talking about the uh, measuring the vector or the distance and the what was the other thing you were talking about, distance and uh, deviation, right? Difference. So you were talking about if we take a word like in English, there are more than 150,000 words, and you want to get the value of a specific word in a vector in the dimension. So how do you compress? What information, do you, so how do you compress it? You said that you compress, you delete some information, but how do you know that which information is valuable and which information is not?
Yeah. Okay. Wait a second. That was the second question, and now I've forgotten about the first one. So,
The collocation of values here.
okay, yeah, yeah, okay. So the whole thing is collocations. Like ChatGPT works entirely through collocations. Now maybe you made a point, which is like, what is a negative collocation? Well, maybe the fact that there's no intuitive understanding of negative collocation is precisely why they don't use negative mutual information. But notionally, it makes sense, right? It's exactly what I was talking about with Dr. Jekyll and Mr. Hyde. If you had some word which, like, imagine that this is the reality we live in. There's a word that if it's in a novel, some other word is not in that novel. Yeah. It's actually easy to imagine, like in the context of historical change, right? Suppose there's an old word for something and there's a new word for something, and they generally mean the same thing. Yeah. Then all the documents that have the old word maybe won't have the new word, and vice versa. So that would come up in principle as negative mutual information, which is to say you can predict, from the fact that one word occurs that another word doesn't occur. But actually, I think precisely because language change, for instance, is not categorical. It's not like every day somebody wakes up and stops saying Davenport and instead says sofa, right? Uh, I don't think it's yeah, anyhow, it turns out, I don't know why, but it's people don't like to use negative mutual information. But I think it does intuitively make sense that two words could have negative mutual information. So the second question is, yeah, I'll just say, how do these things actually work, right? You can even find videos online, right? You're some big company like OpenAI and whatnot, so you buy lots of books, and then you have these machines, and the machines, rip open the books and then scan the books, and then they're reading the book, right? And what it means to read the book is to fill in one of these co-occurrence matrices, yeah. So like, whatever, some article that you wrote, right? I guarantee it that OpenAI and all the other big companies are reading your article, and and then it means that they are changing the weights in their matrix as they're reading your article, right? And then the question is, how do we reduce this high dimensional space? And then the answer is, I don't know, but it's not an interesting question. Like basically, it's like a zip file, like you have your Word doc and it's whatever 50 megabytes, and then you zip it and it's only 2 megabytes. That's exactly what it's doing. Like, I mean, I think I can say this with some confidence. That's exactly what it's doing, right? That's file compression. It's saying, how can I uh, reduce redundancy in this encoding? Yeah. And the redundancy that I was talking about was zeros, lots of zeros in your high dimensional vector space. Yeah. So you just find some geometrical way of folding the space in on itself where you take advantage of the fact that there are so many empty spots. Yeah. And then I like the way I imagine it in my head is like you have some fabric that's like that's the English language as ever used, and it's sort of billowing through this high dimensional space. And then I say, okay, how do I push this billowy fabric into a smaller space? Yeah. And how do you do it in a way that you know that you're not losing important information? I think to some extent they have ways of testing this, but to some extent they don't. Yeah. And you just shrink it and you hope that you haven't lost anything important. Yeah. And this is like one of the ways that DeepSeek is different than ChatGPT. For instance, is they have they're in a much smaller dimensional space, and you can actually get like really like cheap versions of all these LLMs to run locally, where they put them in increasingly small spaces. But generally, the smaller the dimensionality, the less it actually knows. Yeah.
So by redundancy, you meant that if, for example, quick appears with quick um, person or quick chore or quick, so the you see that the items on the left or on the right, how much common they are, or do they belong to the same class or not? So do you mean by redundancy that when it's redundant like that, information from the distribution on the left, on the right, and how much similar are they, and they become redundant, so it's easy to compress those kind
No,
of
that's
information?
not how you should think about it. The way you should think about it is that it's kind of like this. Suppose that I have one book in one corner of my house and one book in another corner of my house. And there is in principle at least, there is information contained in the fact that those two books are in different corners of my house. Like maybe I was reading one in the bathroom and I left it in the bathroom. So the fact that I left it in the bathroom is containing information about where I was, yeah? But then I say, I don't care about that information. So I just put the one book on top of the other one. And now they take up a lot less space. Yeah. So what they actually do is you look at some part of the matrix that's full of information, and then a part of the matrix that's just all zeros. Yeah. And then some other part of the matrix that's full of information, and some other place that's all zeros. And you just take one part that's full of information and stick it in the part that's full of zeros. Basically, that's what they do. Yeah.
Okay, so we have a comment in the chat box that I would like to share a comment. Used to think that the signified referred to the object, but now I understand that it actually refers to the meaning. Thank you for clarifying this point. It gave me a thoughtful insight into how meaning is constructed in a logical way and how it can even be interpreted mathematically.
Thank you for this very kind comment. And this is, I would say, if the one thing that you want to take away, it's that this idea that the word tree refers to a tree in the real world, that is Plato's idea. Yeah, it is not de Saussure's idea. De Saussure's idea is that there's a thing called a sign, and then it is just one thing, and it has two aspects, like size and the weight or something, that always go together. And those are the signifier and the signified.